Intuitive derivation of the $N term. To start, let's quickly recap what we've covered in our previous lessons. We learned that an arithmetic progression, or an AP, is simply a sequence of numbers where the gap, or the difference, between any two consecutive terms remains constant throughout the entire sequence. This specific, unchanging value is what we call the common difference, and in our mathematical notation, we denote it with the lowercase letter d. Now, theoretically, if you wanted to find any specific term in an AP, you could certainly do it by just repeatedly adding that common difference d to the starting number. However, as you can imagine, this process becomes incredibly tedious and time-consuming if you are asked to find a term much further down the line. For instance, if you were trying to calculate the 100th term, you wouldn't want to perform 99 additions manually. So, in this subsection, our goal is to move beyond manual addition. We are going to intuitively derive a powerful formula that allows us to jump straight to any position in the sequence and calculate the value of that term directly, without any tedious step-by-step addition. Welcome, everyone. Let's begin our new session on the intuitive derivation of the nth term. A real-world scenario, the annual salary increment. Now that we have established what an arithmetic progression is and why finding a specific term manually can be quite a chore, let's move away from abstract numbers for a moment. To truly understand how the nth term is formed, let's look at a real-world scenario that you might encounter in your professional life. Imagine a person starting a new job. Let's say their starting annual salary is represented by the letter $. Now, to make this an arithmetic progression, the company promises a fixed yearly increment, which we will denote as $, added at the end of every year. Our ultimate goal here is to find a way to determine exactly what that person's salary will be in any given year, which we will call year n. By using this scenario, we can see how the pattern of adding d builds up over time, leading us directly to our formula. Step-by-step breakdown. Now, let's break this down step by step, so we can see exactly how this pattern begins to form. First, let's look at step 1, the first year. In this very first year, the person is just starting their job, so they receive the base starting salary. We can represent the salary in year 1 as simply A. Moving on to step 2, the second year. At the end of that first year, the company provides the first fixed increment, which we called. So, to find the salary for year 2, we take our starting salary and add the difference, giving us a plus. Now let's look at step 3, the third year. At the end of the second year, another increment of d is added to the previous year's salary. If we take our year 2 salary, which was a plus d, and add d again, it becomes a plus d plus d, which simplifies to a plus 2. In step 4, the fourth year, the pattern continues. We take the third year's salary and add the increment one more time. This means a plus 2 d plus d results in a plus 3 d. Finally, in step 5, the fifth year, we follow the same logic and add the increment once more. This brings our salary for year 5 to a plus 4. As you can see, we are building a sequence of values, and in the next slide, we are going to look closely at the relationship between the year number and how many times we've added. Observing the pattern. Now that we have broken down the salary for each of the first 5 years, let's take a moment to step back and look at the big picture. I want us to list these salaries side by side so we can identify a mathematical relationship between the year number and the number of times we have added the increment. If we look at our list, in year 1, the salary is just a, which we can write as a plus 0d in year 2, the salary is a plus 1d in year 3, the salary is a plus 2d in year 4, the salary is a plus 3d, and in year 5, the salary is a plus 4d. Now take a close look at the numbers. Do you see the pattern emerging? Notice that the number of times the common difference, d, is added is always exactly one less than the position of the year itself. For example, in the second year, d has been added only 1 time. In the third year, d has been added 2 times. In the fourth year, we see it has been added 3 times, and by the fifth year, it has been added 4 times. This observation is crucial, because it sets the stage for us to move from these specific examples to a general rule that works for any year we choose. Generalizing for the $N term. If we want to find the salary for the nth year, we simply follow the same logic we just established. Think back to our list. In the second year, we added the increment once. In the third year, we added it twice. Since the increment is added starting only from the second year, by the time we reach the nth year, the increment d has been added exactly n-1 times to our original starting salary, a. Therefore, we can now write a universal formula. The value of the nth term, which we denote as a sub n, can be expressed as a sub n equals a plus the quantity n-1, all multiplied by d. This formula is powerful because it allows us to skip all the tedious addition and jump straight to any term in the sequence. Now that we have looked at the pattern for the first 5 years, let's take a step forward and generalize this logic so we can find the salary for any year we want. Key takeaways. First, remember that we use the letter a to denote the first term of our arithmetic progression. Second, the constant amount added at each step, which we call the common difference, is denoted by the letter. To really understand why the formula works, I want you to visualize the sequence as a series of steps. To reach the nth position starting from the first position, you don't need to jump n times. Instead, you must jump forward n-1 times. Each of these individual jumps represents adding the common difference to your total. So, putting it all together, the general logic for finding any term is this. The value of the nth term equals the first term plus the quantity n-1 multiplied by the common difference. Now that we have successfully derived the formula, let's summarize the key takeaways to ensure you have a solid grasp of the concept. Keep this logic in mind, because in our next slide, we will look at some common pitfalls where students often trip up when applying this very formula. Common mistakes. First, let's look at the error of using n instead of n-1. It is very tempting, when you see the term nth term, to assume that you should add the common difference d exactly n times, which would lead you to write the formula as a sub n equals a plus n times d. However, as we saw in our salary example and our pattern observation earlier, the first term is our starting point. We haven't added any increments yet at year 1. Therefore, we only add the difference for the steps taken after the first term. Always remember, the number of jumps is always one less than the position you are trying to reach. Second, please be careful not to confuse the term value with the term position. This is a very frequent mistake. You must distinguish between n, which represents the position or the rank of the term in the sequence, and a sub n, which is the actual numerical value found at that position. For instance, if I ask for the 10th term, n is 10, but a sub n is the actual salary or number you calculate. And as a final reminder, n must always be a positive integer, as you cannot have a position like a negative number or a fraction in a sequence. Now, before we conclude our lesson, I want to highlight 2 common pitfalls that students often encounter when working with arithmetic progressions. It is crucial to address these now so you can avoid them in your future calculations. Keep these distinctions in mind, and you will find much more success with these formulas.